Section 1.1, Linear Equations and Inequalities. The learning objectives for this section are to solve linear equations, solve linear inequalities, and solve applications involving both linear equations and linear inequalities. Okay, so first we want to look at linear equations and their standard form. Okay, notice here it says, in general, a first degree or linear equation in one variable is any equation that can be written in the form of ax plus b equals 0, where a is not equal to 0. This is called standard form. Okay, so here let's highlight this. We have ax plus b equals 0. This will be standard form. If I take any equation and I can convert it to this form, ax plus b equals 0, it's considered to be a linear equation or a first degree equation. Okay, and the way we determine the degree of the equation is we look at the variable x, in which case it has an exponent of 1. So if there's no exponent written there, it's understood to be 1. Okay. If I have an equation where my variable x, the largest exponent for that whole equation is 1, it's considered a first degree or linear equation. So if I look at the example here, 3 minus 2 times the quantity x plus 3 equals x divided by 3 minus 5. This is a linear equation because if I look at my variables x, in just one moment. Okay, I notice here they both have a degree of 1. Okay, so this is how I know I can put it in standard form, or how I know that it's a linear equation or a first degree equation. Equivalent equations. Two equations are equivalent if one can be transformed into the other by performing a series of operations which are one of two types. 1. The same quantity is added to or subtracted from each side of a given equation. Or 2, each side of a given equation is multiplied by or divided by the same non-zero quantity. So basically we have an equivalent equation if we add or subtract the same number from each side of the equation, or if we multiply by or divide by the same number on each side of the equation. Okay. These series of operations are performed in order to solve an equation for x, or to put it in some standard form or any form that's asked to be given. In this class, we'll mostly use the operations to solve for x, getting x equal to some number, or isolate x. Okay, or we may have the form where x equals some number. Okay, in this case, we'll be determining the solution of the equation. Okay, so here it says to solve the equation x plus 2 all divided by 2 minus x divided by 3 equals 5. Okay, and before we do the series of operations where we add or subtract or multiply or divide, the first thing we want to do is clear the equations of fraction, or clear the equation of fractions. Okay, and the way we do this is we look at the denominators, in which case are 2 and 3, and we determine the least common denominator, or you can just determine any denominator, and multiply that LCD, or that least common denominator, to both sides of the equation. Okay, so in this case here, I'm going to write each denominator as a prime factorization, in which case 2 and 3 are already prime. And in order to determine my least common denominator, I'll take every term from the first denominator, okay, and then I'll come down to the second denominator and only include what's missing. So in this case here, I have a factor of 2, but 3 is also missing, and so I'll multiply by 3. So my least common denominator is going to be 6. Okay, I'll take 6 and multiply 6 to both sides of my equation, and this will allow me to get rid of the fractions within the equation, and make sure you're multiplying both sides of the equation by 6. Okay, so here we have 6 times the quantity x plus 2 divided by 2 minus 6 times the quantity x divided by 3 equals 6 times 5. And so if I simplify this, 6 divided by 2 is 3. So I'm left with 3 times the quantity of x plus 2. Here I have a negative 6 divided by 3. So if I simplify this, a negative 6 divided by 3 is a negative 2. So I'm left with a negative 2 times x equals, in this case, I don't have anything to cancel, so I'll just multiply 6 times 5, which is 30. Okay, so I'm going to go ahead and clear the equation of fractions, of parentheses, by distributing. I have 3 times x plus 3 times 2 minus 2 times x equals 30. Okay, and I want to combine like terms. So I have 3x minus 2x, which is just x plus 6 equals 30. And now I want to solve the equation. So I'm going to apply one of the two series of operations. I'm going to subtract 6 to isolate this x. So if I subtract 6 on the left side, I need to also subtract 6 on the right side. And so I get x equals 24. So 24 is the solution to this equation, or basically 24 represents x. Okay, if I want to check this, I can take 24 and go in and replace 24 with all the values of x. And if it gives me a true statement, then I know this is a solution. Okay, so I'm going to take this equation here and check. Since I know that x equals 24, I should be able to replace all of my values of x with 24. So I have 24 plus 2 divided by 2 minus 24 divided by 3 equals 5. And so here 24 plus 2 gives me 26 halves. Minus 24 divided by 3 is 8 equals 5. 26 halves is just going to be 13 minus 8 equals 5. And so in this case here, 13 minus 8 is 5, and 5 does equal 5. So I have a true statement. Therefore, my solution of 24 is the correct solution. Solving a formula for a particular variable. In this example, it says to solve m equals n times t plus n times r for n. Notice here on the right side, we have n times t plus n times r. Both of these terms have a common factor of n. So since we're solving for n, here we'll go ahead and factor those n's out of each terms so that we can then isolate n. So let's factor n from both terms. We have equals n times the quantity. And in this case here, if I'm factoring out an n, I'm basically just dividing each of these terms by n. Okay. So if I divide nt by n, I'm left with t, because the n's will cancel or they'll both become 1s. Plus nr divided by n, I'm just left with r. Okay. So let's bring down the left side m. And so now, in order to isolate n, notice here the quantity t plus r is multiplied to n. So in order to solve n or isolate n, I'm going to do the opposite of multiplication and divide both sides of the equation by t plus r. Okay, and so the two t plus r's will cancel, or they'll become 1 over 1. And so I'm left with n equal m divided by the quantity t plus r. So my solution for n is m divided by t plus r, or I have the formula n equals m divided by t plus r. Okay, let's look at linear inequalities. It says if the equality symbol equal is a linear equation and is replaced by an inequality symbol where we have less than, greater than, less than or equal to, or greater than or equal to, the resulting expression is called a first degree or linear inequality. Okay, so notice here we know it's first degree because if we look at our variables x, we notice that we have a degree of 1 for each one. Okay. So So this is going to be a linear inequality, and we know it's an inequality because of the expression here of an inequality symbol. Okay, solving linear inequalities. Basically, when we're solving linear inequalities, we solve them the same way we do solving equations. There's just one thing that we have to be careful of when solving inequalities. Okay, whenever we multiply or divide both sides of the equation by a negative value, we'll always have to flip the direction of the inequality symbol. So notice here it says the sense of the inequality reverses if we multiply or divide both sides by a negative number. For example, if we look at a -2 greater than a -9, and we multiply both sides of the equation by 3, we'll get a -6 is greater than a -27. Okay, so let's look at that. We have -2 times 3 greater than -9 times 3. Notice that it's we've maintained equality because we did multiply 3 by both sides. We'll get -6 is greater than -27. Okay. Here it says the sense of the inequality remains the same. So in this case, we multiply by a positive value. But if we multiply both sides by a -3, okay, we must write 6 is less than 27. Okay, so let's look at that. Here, if I have -2, -2 is greater than -9, and I multiply by a -3 on both sides of the equation. Okay, I need to flip the direction of the inequality symbol. Okay, so by multiplying a negative on both sides of the equation, or dividing, but in this case multiplying, we want to flip the direction of the inequality. And so we have -3 times -2 is a +6. It's less than -9 times a -3 is a +27. Okay, and in this case, we know this is a true statement because 6 is less than 27. Okay, so the sense reverses, the sense of the inequality reverses after we multiply by a negative number. Okay, so let's look at an example for solving a linear inequality. Okay, to solve this inequality, the first thing we want to do is remove parentheses. So let's distribute the 3. Here we have 3 times the quantity x minus 1, so we have 3 times x minus 3 times 1. It's less than, here we're going to distribute the 5. We have 5 times x plus 5 times 2. Let's bring down our minus 5. Okay, on the right side, we want to combine like terms. So in this case here, plus 10 or a positive 10 minus 5. We can simplify that to make that a positive 5. So here we have 5x plus 5 on the right side. And let's bring down 3x minus 3 on the left. Okay, so here I want to get the x's on one term and the constants on the opposite side. So now we're going to apply one of those operations where we add or subtract or multiply or divide. In this case, we will always want to do the opposite of what's being done within the inequality. So I like to move the x on the left side because it makes it easier to graph later. So in this case here, I'm going to take this 5x and do the inverse of this positive 5x. And I'll subtract 5x on both sides of the equation. Okay. So on the right side, it cancels because a positive 5 minus 5 cancels. We have 3x minus 5x on the left is 2x, but a negative 2x. Bring down our minus 3, less than positive 5, and we can just bring down 5. Okay. So we want to isolate the negative 2x first in order to isolate x. And notice here I have a minus 3, so I want to do the inverse of subtracting 3, and I want to add 3. But to make sure it stays equal, I'm going to add 3 on both sides. Okay, so the 3's canceled on the left side, and we're left with a negative 2x less than 5 plus 3 is 8. And in order to solve for x here, we know it's -2 times x whenever it's written side by side. So I want to do the inverse of multiplying x by -2, and I'll divide x, or -2x by -2. Okay, so I divided by a negative. I want to take my inequality and change the direction of the inequality. And so -2x divided by -2 leaves me x. A divided by -2 leaves me 4. Sorry, -4. So let's fix that. Okay, so if you're asked to give an interval notation, in this case here, and I'll go ahead and write it out. The easiest way to give interval notation until you get used to giving it is to first go ahead and graph your inequality. So in this case here, you can write all your number lines. I'm just going to express -4. If I know x is greater than -4, it's going to be all values to the right of -4, say 0, 1, 2. So I know these values are greater than -4. And the way I express that x is strictly greater than -4, meaning -4 is not included, is I put a parentheses there. Okay, and so in order to give my interval notation, I'm going to write my leftmost endpoint of my inequality expressed. So the leftmost endpoint starts at -4 with a parentheses, and it goes to the arrow which expresses a positive infinity. Okay, so my interval notation is open interval -4 to infinity. Okay, if I'm asked to give set builder notation, let's put this to the left. Okay, I have the set of all x such that here I'm going to put my inequality here, x greater than -4. Okay, so this gives us the set builder notation, and this gives us the interval notation. In here, we'll mostly use the interval notation. So let's look at interval and inequality notation. Okay, so it says here, if A is less than B, the double inequality, and let's highlight that. Okay. X greater than A and X less than B means that we basically read this portion first, X is greater than A, and this portion second, X is less than B. Okay, and this just means that X is in between A and B. So if I were to graph this on the number line here, my left endpoint would be A, my right endpoint would be B. X is in between, so I shade everything in between A and B. And in this case, it's strictly greater than A, so I'll do a parentheses here to express that A is not included. It's strictly greater than, and strictly less than B. So I'll draw parentheses here at B. Okay, and so if I were to give interval notation, the interval notation represented by X greater than A and X less than B would be given as the left endpoint to the right endpoint. So I have a parentheses, A, comma, B, parentheses. Okay, and both of these represent the inequality represented here. Okay, so it says here, interval notation is also used to describe sets defined by single or double inequalities as shown in the following table. Okay, make sure you look over this table and you understand how to express an inequality or an interval in interval notation or set builder notation, or just given as an inequality. Okay, so just make sure you understand how to express any inequality. Okay, so here we'll look at two examples dealing with interval and inequality notation in line graphs. Okay, so for part A, we have basically an open and closed interval here, -5, 2, which represent our endpoints, but this implies that X is greater than -5 or equal to, so greater than or equal to -5, and strictly less than 2. So if I were to express this, it basically means that X is in between a -5 and 2, but this square bracket implies that X is greater than or equal to -5 And this parentheses implies that x is strictly less than 2. Okay, and then if I were to graph this on a number line here, I'd have my left endpoint -5. This would be about 0. This will be about 2. So here I have -5 to 2. I'm going to shade everything in between. I want to express a square bracket here for x greater than or equal to -5, and a parentheses here to represent x less than 2. Okay, let's look at B. Okay, for B, we have x is greater than or equal to -2, and we want to express this in interval notation and graph. Okay, so to express this in interval notation, I would suggest to first graph it. Here we have x greater than or equal to -2. I have -2 on a number line. If you want to write all the numbers, you can. Here, I don't usually. Okay, but if x is greater than, that's going to be everything shaded to the right of -2, or equal to, we want to express with a square bracket. So if I graph this on a number line here, basically I can take the graph represented and start with the leftmost endpoint, -2, expressed with a square bracket, up to infinity, and I'll always write a parentheses for infinity. Okay, and this will give us our interval notation, and we already have our graph. Okay, let's look at the next slide. Okay, so here we want to look at the procedure for solving word problems. Okay, and in this case, we'll look at the procedure for solving word problems dealing with linear equations and linear inequalities. Okay. Okay, so step 1 says to read the problem carefully and introduce a variable to represent an unknown quantity in the problem. Okay, so the main thing we want to focus on is read. Let's highlight that. And introduce a variable to represent an unknown quantity. Okay. 2, it says to identify other quantities in the problem, known or unknown, and express unknown quantities in terms of the variable you introduced in the first step. Okay. So from step 2 here, we want to express any unknown quantities in terms of the variable introduced in the first step. Okay. And then you'll also express your known values. Okay, step 3, write a verbal statement using the conditions stated in the problem, and then write an equivalent mathematical statement. Okay, and this statement will just be your linear equation or your linear inequality. So here we're going to highlight, write a verbal statement using the conditions stated in the problem. And then write an equivalent mathematical statement, okay? And that'll just be an equation or an inequality representing your verbal statement. Okay, 4, solve the equation or inequality and answer the question posed in the problem, okay? Okay, so you want to solve the equation or inequality and answer the question posed in the problem. So answer the question posed, okay? So in this case here, if I have x is equal to 2,000, but it asks me for some other expression other than what x represents, okay? If I answer 2,000, then my answer will be wrong because they're asking me for another value. So just be mindful to always answer the questions, the problem's question, okay? In step 5, check the solutions in the original problem. So here, check your solution in the original problem. If you check it in the original, then you'll always know that it's correct because there are cases where you may set up a word problem and do step 3 wrong. So maybe you'll take the verbal statement and write the wrong mathematical statement to represent that. If you check it in the original wording of the problem, you'll catch this because you can solve the wrong equation properly. But if you check it in the original wording of the problem, you'll know if you've set up the right equation and also solved correctly. Okay, let's look at the next slide. Okay, so this is an example of a break-even analysis problem. It says a recording company produces compact discs, CDs, and a one-time fixed cost for a particular CD is $24,000. This includes costs such as recording, album design, and promotion. Okay. The variable cost amount is $6.20 per CD, and this includes the manufacturing, distribution, and royalty costs for each disc actually manufactured and sold to a retailer. Okay. The CD is sold to retail outlets for $8.70 each. How many CDs must be manufactured and sold for the company to break even? Okay, so when you're reading the word problems, what I would suggest to do first is to underline the problem's question. Okay, just so you can make sure when you're solving all of your work, you're mindful to answer what they're asking you for. Okay, so step 1 says to read the problem carefully and use a variable to represent your unknown quantity. Okay, here it asks us how many C's must be manufactured and sold for the company to break even. So we don't know how many CDs must be manufactured. So we'll let X represent this. Okay, so step 1. Okay, let's let X represent the number of CDs that must be manufactured and sold. Okay, so step 2 says to express any known quantities and also to represent any unknown quantities in terms of the variable in the first setup in the first step. Okay, so in this case here, our known quantities here, it says that a one-time fixed cost is $24,000. So I'm going to say here the fixed cost equals $24,000. Okay, and then it says that the variable cost is $6.20 per CD. So here, let's write this. Our variable cost equals $6.20 per CD. Now, we don't know how many CDs are sold, so our variable cost depends on that. And we'll say if it's $6.20 per CD, we'll say it's $6.20 X. Okay. Okay. And then it says here that the CD is sold to retail outlets for $8.70 each. So basically, this represents the revenue, and we're already given the cost. So anytime you're trying to determine the cost, let's go ahead and, I'm getting ahead of myself. So that's step 3. Okay, so step 3 says to write a verbal statement representing the conditions represented here, and also a mathematical statement. So a verbal statement here that we can say, we're trying to determine the number of CDs that have to be manufactured to break even. So in order to break even, here, let's circle that. In order to break even, the total cost must equal to the revenue. Okay. And the way we determine the cost, we look at the fixed cost and the variable cost and take the sum of those two. And then to determine the revenue, we determine how much we're selling, whatever we're producing per item. Okay. So I'm going to say here the total cost, the verbal statement, is equal, or we'll say must equal, the total revenue to break even. Okay, so in order for them to break even, we know that they must equal. So we'll say that the cost must equal the revenue. Okay, and if the cost must equal the revenue, in order to determine the cost, I'll do it over here. We're going to look at the fixed cost, which is $24,000. Okay, plus the variable cost, which is $6.20 per CD. So $6.20 times X. And this has to equal the revenue, which we know is going to be $8.70 per CD. And so in this case here, we don't know how many CDs, so it's $8.70 X. Okay. And so you could also put this above here in number 2. You can say the revenue is equal to $8.70 x. Okay, so now we have a mathematical sentence that we can solve for. Notice that this is a linear equation because our degree of our x's, or our exponents for our x's, are 1. Therefore, our degree of our equation is 1. So we know it's a first degree equation, meaning it's a linear equation. Okay, so in this case here, I'm going to solve this by getting the x terms together, opposite of a number, and then isolate my variable altogether. Okay, so here I have plus $6.20 x. So I'm going to do the inverse, subtract $6.20 times x on both sides of the equation. Okay, and so here I have 24,000 left on the left side. And then I have $8.70 divided by, or minus $6.20. So we have $2.50 per CD times x. Okay, and so here I want to isolate x, so I'm going to divide both sides of the equation by 250. Okay, and this gives us here x on the right side is equal to 24,000 divided by $2.50, or 2.5, will give us 9,600. Okay, so in this case, we set up the equation. I'm going to squeeze in step 4. Solving this equation was step 4. And then step 5, we want to check. So here, let's squeeze in check. And in order to check this, we want to check it in the original wording of the problem. Okay, so above it says that we know the fixed cost was $24,000. The variable cost was $6.20 per CD. So here I'm going to plug in 9,600 CDs into the cost function. Okay, and so in this case here, my cost function, let's move it up here. Okay, so let's say our cost is 24,000 plus, oh, I need more room. Okay, so let's move it here. So the cost is 24,000 plus $6.20 times 9,600. Okay, and so this will give us our total cost function, or our value of our total cost. Okay, and so this gives us a total of $83,520 to represent our total cost. Okay, for our revenue, we know that our revenue is $8.70 for each CD, and so we have $8.70 times 9,600. Okay, and so this gives us $83,520. Okay, so we know since the cost and the revenue are equal, we know we've solved this correctly, and we know that we've determined the break-even point where the cost and the revenue are equal. Okay, so now I can make sure I answer my problem's question. Here it says how many CDs must be manufactured and sold for the company to break even. We must sell, or the company must sell 9,600 CDs. Okay, so I'll squeeze it in here. The company must sell 9,600 CDs. Oh, let me not put a dollar sign there. CDs to break even. Okay, and that's answering our problem's question. Okay, so we've covered an example of how to solve word problems. You'll have different types of word problems, but just be mindful in step 2 to write any unknown quantities, any additional unknown quantities in terms of the first variable, okay, or the first unknown quantity. Okay, that pretty much summarizes the lesson. If you have any questions, just email me. we've covered everything for this section, all learning objectives. So we've covered how to solve linear equations, how to solve linear inequalities, and how to solve word problems that contain linear equations or linear inequalities. Okay.